So, shall we start? Hi, everybody. So, we ended up talking about the issue with very deep. What is that? Okay. So, we ended up discussing the issue with very deep convolutional neural networks, right? So this was where we ended last time. So you remember the challenge, right? The challenge of ImageNet, and people started to just win by deep learning in it since 2012. And then the point was that if we go deeper, we always should see better result. But they started to see something else when they went super deep. And then this was the result last time that I showed you. So this was the result when you were training a 20-layer VGG-like CNN. This is a 20-layer CNN and 56-layer CNN. And then you see, I mean, based on that one, people concluded that there is something wrong happening inside that architecture. And do you remember what was the issue? Why these results are not very promising? Why isn't that simply an overfitting? Do you remember that? Yeah, go ahead.
Because it was bad. It was worse in both training and testing.
Exactly. So in the training, you are also seeing the worst performance. This shouldn't be the case. So in training, you should see a better performance. And then when you get to the testing, it doesn't work fine. Then you would say it's overfitting. So it was not overfitting. It's actually issue with the model itself. So the model is not getting trained properly, or it's not performing well. So we cannot perfectly match it to the data. And then the question is that when we can do it with a simpler model, a shallower model, why we cannot do it with deeper model? And the conclusion was that the issue is basically coming from the vanishing gradient. Okay, so now what is vanishing gradient idea? So we talked about these guys. So the first two winners, they were not really deep neural networks. They were basic approaches, shallow approaches. And they won. These numbers that you see here are the error percentage they were returning. So you see that in 2010, we were happy with 28% error. So we wanted roughly somewhere around 70% accuracy on ResNet. Nowadays, I mean, you're getting below 4%. Yeah? So people at this point, this was the first time AlexNet won in 2012. And you see it was a huge drop. From 25%, we got into 60% error. This was the first deep neural network winning. And after that, it was always deep neural network. So you see here, there was a drop. This was no change in the number of layers. But we started to go deeper. And then we expected to always see that as we go deeper, we are actually getting much lower, right? But this was not really happening. So you see that this red dash is somehow proportional to the number of layers, to the depth of network. And we are going up. As we go up, we are just coming down in terms of error, better accuracy. But this was the point where people tried to do that experiment I showed you. And it was not working very well anymore with deep neural networks. So, okay. Isn't that too dark today? Don't you have the feeling that? Okay. Or it had been always like that and I didn't notice. Anyways. Okay. So that was the issue. So the problem people started to talk about was the idea of vanishing gradient. As I told you, this was somehow being talked about for quite some time. It was not immediately seen in deep neural networks in terms of depth, but as we're going to see in the next chapter, it was actually somehow seen before when people were trying to do the training over time. When we get into sequences, the recurrent neural networks, vanishing gradient was something now. But at this point, people started to say, OK, again, we are going very deep, and this is making the vanishing gradient. What is the idea of vanishing gradient? So when you are computing the gradient, if you just look at the backpropagation from a very high-level perspective, you basically compute, go forward, and then at the very end, you compute one gradient, right? And this gradient is just propagating backwards through your network, right? And each time it goes through network, it's getting multiplied with a bunch of other gradients, right? Now, if you have too many of those gradients, and these gradients are small numbers, then as they get multiplied more and more, they're going to get smaller and smaller. And then at the end of the day, you want to update with those gradients. They are very small numbers. They're essentially not doing any update. But the point is that they are somehow updating some weights in the deep layers. They are pretty much doing no update on early layers. And this is the issue that could make your network stop getting trained. Okay? So this is the whole idea. But of course, if you want to understand it, you need to see a bit of formulas. So we could start with just getting like a super deep convolutional neural network and try to break down the backpropagation for that. But this is not a good idea. So I'm going to get the help from my very good friend. So you know him, right? Of course. So Einstein has a saying. He says, like, everything should be made as simple as possible, but not simpler, right? And this is what we're going to do here. So we're not going to discuss it for a general neural network, but we can do it for a very dummy neural network. And once you understand that, then you're going to understand it for any, I mean, you can extend it easily in your mind for any neural network. So let's consider one dummy example. So one dummy feed-forward neural network. And this neural network has just one scalar input. So you have one scalar x, which is going to go through the network. Okay? And then it has L different hidden layers. So first input x is going to the first, second, so L. And then you get the output. And every single hidden layer is again of width 1. So it has only one neuron. So simply speaking, you get your input, you pass it like in a sequence of neurons, and finally you get your output. So I assume that all the neurons are being activated by activation function f. This means that starting from x, I'm going to multiply with one weight. Then I have the activation function. The output is getting again multiplied with the second weight, activated, and so on, till you get to the very output. So this is the red one is the output layer. So you basically have L of these hidden layers, and this is the output layer, and theta is the output, the activated output of the output layer. Okay? This is a dummy neural network, I do know, but this is enough to understand what is the vanishing gradient issue. Okay, now let's start by passing some guy x through this network. If I do that, how do I do it? I mean, that's quite easy, right? So I'm going to have x. If I have x, I have first w1 times x. This is my linear transform. And then I'm going to activate it, pass it through f, right? And then this is going to be my y1. So y1 is basically the guy at the output of the first neuron, right? Then I'm going to pass it through the second neuron. So what I got out of the first neuron, I'm going to linearly scale it and activate it through in the second neuron. And I keep on going till the last guy. So this last yellow neuron you see here is the one which is computing YL for you. Yeah? So this is the last guy computed. Okay? And then out of that, you're going to compute your theta, which is, again, you get your very last hidden output YL, and you multiply it with the weight WL plus 1. This is the weight of the output layer, and then you're going to activate it, right? So very simple, right? Okay, now forward pass is not the issue. For us, the issue is the backward pass, right? So the gradient is vanishing, so something is happening inside backpropagation. So let's just start with the backward pass. And when I'm showing theta dash, exactly like what we did in chapter 2, theta dash is simply the derivative of your risk function or your loss function r hat. Here is the sample loss. The derivative of the sample loss with respect to theta. Anything with dash is the derivative of the loss with respect to that variable. Okay? Now, given this one, if I want to move from theta backward in this neural network, what would be the first guy that I should compute the gradient with respect to? So I have here x. then I have, after doing f times w1, this guy, I'm going to get y1, then I'm getting y2, and so on till I get yl. And then out of this yl, I'm getting theta. So this is basically the computation graph, right? And out of theta, I am computing the loss, r hat, right? And now I do know what is the derivative of loss with respect to theta. How should I go backward? What is the next thing? YL, right? So I'm going to go backward here, right? So if I want to compute the derivative of r hat if I have this guy, the next thing I need to compute is the derivative of r hat with respect to YL, right? And how do I do it? I use chain rule, right? So let's just write down the chain rule. So theta is here. Theta is a function of YL. So if I want to compute the derivative with respect to YL, I'm going to get the derivative with respect to theta. This is what I already have, times the derivative of theta with respect to YL, right? Now, how do I write this derivative? Theta, can you tell me what is theta? Is an activated function in terms of YL. What is it? WL plus 1 times YL, right? Now, if I want to compute d theta, let me clean this one. If I want to compute d theta to d YL, what is it? Let's do it once, then it's over. Derivative of theta with respect to YL, what is that? It's going to be the derivative of this theta with respect to the whole argument. So it's going to be f dot at what point? WL plus 1 times YL times, what is the other term? WL plus 1, the derivative of argument, right? So WL plus 1. This is the derivative, right? Everybody's clear? So I'm going to replace that derivative here. So I'm going to put it WL plus 1 times the derivative of the activation function, right? At the particular point. Clear? OK, great. Now, the next thing that I need to compute is derivative with respect to YL minus 1, right? So I'm going to go backward again. Derivative with respect to YL minus 1. It's again the same thing, right? It's going to be the derivative with respect to YL, which I already have it here. And then I multiply it with derivative of YL. OK, here is a typo. The blue one should be YL minus 1, right? So it's a typo, sorry. So derivative of YL with respect to YL minus 1. Yeah? And you can again say, what is this guy? The derivative of YL with respect to YL minus 1. Look at this expression. It's exactly as before, right? So it's going to be the weight of layer L, WL, times the derivative of this activation function, right? Everybody's clear? Yeah. So I'm going to replace it like this. And now, this YL dash, this is the derivative with respect to YL. I already have it in the previous line, right? So I'm going to replace it here, right? OK? So I'm going to replace it here. So I'm going to have the multiplication of the weights times the multiplication of derivative of activation functions, right? Now, what's going to happen if I keep going backward till the very beginning? How many of these terms I do have? I'm going to have L of these terms. How many of these terms I would have, these weights? Again, L different weights, right? So if I keep on going backward like I am at this particular neuron, and this neuron is computing y2 out of y1, which is the output of this guy. So now I want to compute the derivative of loss with respect to y1. Of course, I have already backpropagated up to y2, right? So I do know what is the derivative of r hat with respect to y2. I only need to multiply it with this guy, derivative of y2 with respect to y1, which is going again to be the weight of that layer times the derivative of activation function. And if I keep replacing the previous terms for the derivative, you can simply see that it is going to be this guy, right? So you have all of the weights up to the second layer, up to W2 included here, times their derivative of the activation, right? Everybody's cool? Yeah? OK. Now, what do I need at the very end of the day? At the end of the day, I need to compute the derivative with respect to weights, right? So I need to know derivative of my loss with respect to all weights, W1, W2, so on. So say I want to compute the derivative with respect to the very first weight, the weight in the very first layer. Okay? How can I write it down? I could say that, OK, I do have the derivative up to y1, right? If I have the derivative with respect to y1, then I can simply compute the derivative with respect to w1 in terms of that guy, right? So I'm going to open it up in this form, again, the chain rule. So derivative with respect to weight 1 is derivative with respect to y1, which is immediate function of w1, because y1, look at this line, this item here, y1 is a function of w1 times x, right? So I'm going to write it down in this form. Derivative with respect to w1 is going to be the derivative with respect to y1, this guy, times derivative of y1 with respect to w1. Do I need to include any other term here? Is there anything else which is an immediate function of w1 in this network? No, right? So there is no guy here in between which is getting w1 from any other way, right? So the only way w1 is contributing to the loss is exactly through this neuron. And this is the only term that I need to keep here, right? Everybody's cool? It sounds easy, but once it's cool, then the ResNet going to be, again, clear for you. OK? Now, if I do that, then basically this derivative of y1 with respect to weight 1, it's going to be, again, derivative of the activation function times, what is the term that shows up there? X, right? OK, so it's the same thing. Instead of weight, I have x, right? So it's going to be x times the derivative of the activation function. And now I do have the derivative with respect to y1. I computed through backpropagation, right? I started from very end and backpropagated towards beginning of the network. So I'm going to replace that guy, and this is going to be the term that I'm going to get as the derivative of the weight, right? So this term, look at it. How many derivative of activation functions do I have? L plus 1. I have derivative of activation function for L plus 1 times. Here L times, and here once. And I have L different weights participating in that, right? Correct? OK, great. So now I can just look at this term, this derivative with respect to weight 1, to be the derivative that I started with. So the derivative at the very, very output, this is the immediate derivative I compute to start backpropagation, right? This guy, once it's backpropagating over the network, is somehow getting multiplied with this term. And this whole multiplicative term is what is accumulated through backpropagation, right? Now, let's consider two cases. The first case that we want to consider is that we have a sigmoid function, sigmoid activation, right? And all the weights that we have inside this neural network are smaller than 1, OK? There are some numbers between 0 and 1, OK? Now, what is the derivative of sigmoid function? Derivative of sigmoid function, do you remember it? What is it? It's going to be sigmoid function itself times 1 minus sigmoid function, right? This is the derivative. Sigmoid is between this term 1 minus sigmoid is between. So this term is going to again be between 0 and 1. So this guy is smaller than 1 definitely, right? It's never 1, right? It could be very close to 1, but it's never 1, right? Great. So this guy, sigmoid, has a derivative which is always smaller than 1 for any x. It doesn't matter what is the input, it's always smaller than 1, right? And I told you that all my weights are smaller than 1, right? So I could say that there exists one number a which is smaller than 1. It could be very close to 1. It could be 1 minus 10 to power minus 10, I don't know. It's like 0.9999999 forever. It could be, but it's not 1, right? Correct? Okay, there exists this a such that every derivative that I have here in this expression, every derivative is smaller than a. Every weight here is smaller than a, right? Correct? Okay, so if I do that, then I can simply bound what I have as the derivative here, the derivative of r hat with respect to the first weight, the weight of the first layer. I can write it down in this form. Everybody agrees? So it's going to be smaller than that one. Because every single term here showing up in this multiplication is smaller than 1, right? Smaller than a, right? And I just replace a with everyone. I would say it's going to be smaller than that term, right? And I have L plus 1 different activations, so it's going to be L plus 1. And I have L different weights, so another L term, so it's going to be a to power 2L plus 1 times x times the derivative, the gradient I started with. Cool? Questions? Now, what's going to happen for this term if I just send L very large? If I just send it to infinity, what's going to happen to this term? It goes to 0. So does the gradient, right? When the bound goes to 0, it means that the gradient is between 0 and that 0, so it's going to be 0, right? So if you send this guy to infinity, if you just increase the number of layers you have, this gradient term is going to go to 0, right? Everybody's clear? This is what we call it vanishing gradient. It is vanishing through depth, right? So the gradient is getting smaller and smaller through depth. Clear? Now, one point that I just want you to get very clear here is that if I look at this, if I have a huge neural network, if my number of layers is huge, the gradient of this term, does it go also to 0? No. The gradient of these deep layers are not going to 0 because they are very close to the output gradient, right? So the gradient is getting there. The gradient of the initial layers are getting to 0, right? So when you do update, your initial layers are not getting updated, right? But your end layers are getting updated. Correct? Do you want this? Do you think this is a good idea? No, because the main, like in the CNN, the main layers which are extracting right features for you are the early layers, right? If they are trained well, then the later layers could just build upon that, right? So this is the issue. It doesn't mean that all the gradients are going to 0. If all the gradients are going to 0 together, that is easy. We scale all the gradients together, right? We multiply all the gradients with a huge number. But this is not the case. This guy at the very end is not going to 0. This guy at the beginning, it is going to 0, right? Everybody's clear? Okay, so this is the idea, this is the issue that we call it vanishing gradient. We would say that, if you want to talk technically, when you do backpropagation, this accumulation term concentrates at 0. It means that most of the time is just randomly changing, but most of the time is around 0. And this means that when you are doing the updates by gradient descent, most of the time you are just updating with something around 0, right? Which means that you are pretty much doing nothing, right? Okay. This is the idea of vanishing gradient. We can consider an alternative case. The alternative case is that we assume that all the activations are ReLU functions. Okay? If you have ReLU function, and for the moment assume that all the input is positive, all the weights are positive and are more than 1, and then if this is the case, then all the features are going to be positive as well, right? So when everything is positive, this means that the derivative of my ReLU function is going to be 1, right? The derivative of ReLU function is always 1, right? At the positive side, at the negative side is 0, correct? So it's going to be 1. That's fine. And all the weights that I have are more than 1, right? Yeah. Sorry? I just assume for the moment. Yeah. Just consider the case like you started, you just initialize your network with weights more than 1. Okay? Now, if this is the case, then what's going to happen? I can again say that there exists one A, a tiny bit more than 1, right? Again, it's not 1 exactly, but it's going to be 1.000000 forever 1, okay? Just a tiny bit more than 1, okay? That A exists such that every weight that I have is more than this A, right? Every weight that I have is more than the value A. So it could be a tiny bit more than 1, but it's there. Now, if I do that again, I can now write this gradient. I can bound it from below. So I could say every weight I have here is more than A. I have L of them, so AL is going to show up here. All the derivatives are 1, so there is nothing here, so it's basically 1. And I have X and the derivative, or the output gradient also here. So now what is happening here? The thing that is happening here is that my gradient is getting more than this term, the output gradient, the input value, and then A to power L, that number larger than 1 to power L. Now, if I keep my neural network getting deeper and deeper, L goes to infinity, what's going to happen to that term? It's going to go to infinity, right? So it's going to go to infinity. This means that my gradient is going to go to infinity. This is the behavior, we call it exploding gradient. So your gradient is just exploding up. It's just booming up. It goes to saturate into some high value, right? So this is another kind of behavior. So in this case, your gradients at the input layer is always concentrated at the saturation value, right? So whenever you just go back, your computer can save large numbers up to a point. When you just pass the floating precision of your computer, then you're going to be the maximum value, right? And technically it's infinite, right? Always, right? Yeah.
So we intentionally fix a sigmoid, but the weight is greater than 1, and weight
Yeah. Yes, yes.
is
Yeah. But the point here is that once you have that property, then you are updating all of your weight. I mean, that weight W1 with an infinitely large step, and this means that you are keeping in that situation forever, right? Once you start to exploding gradient, you cannot get back, right? Same thing with vanishing.
Let's say the value, the gradient itself equals to 1.
Yes.
Okay. No.
Yeah, that is not the issue. The weights themselves are the issue, right? Yeah. So now, when we go deep, moral of the story here is that if you go deep inside your neural network, once again, at the layers close to the output layers, you have no problem because there is no much depth, right? The gradient can easily propagate up to that point, right? The issue is happening at the very early layers because the gradient is just propagating very deep backwards. And because of that, your gradient could be either vanishing or it could be just exploding, right? So the gradient at the early layers, they would concentrate at 2 points. They're going to be either 0 or they are going to be very large. Clear? Now, in practice, vanishing is happening more often as compared to the exploding. And the reason is that most of the time, I mean, the weights that you have inside your network, because of the normalization you do, they're usually small. And you usually use activations, which are giving you like gradients either 1 or close to 1, right? So because of that, vanishing is more often happening. And one other point is that when we have an exploding gradient, we still have gradient, right? We can clip it, for instance. We could say, like, if it is larger than something, we're going to keep it like 10 or something like that, right? But with vanishing, you cannot do anything. So this is why vanishing is a more challenging issue. And one other point that we see here is that if we don't want this happen, if we don't want to go to 0 or infinite, what is the other option? The other option is that all the weights and all the activation derivatives are being 1 exactly, right? So when they are exactly 1, then your gradient is always going backward the same, right? Just look at this term here, right? If all of my weights are 1, all of these derivatives are 1, then the term that is left is the derivative of output times the input, right? There is no vanishing or exploding happening here, right? So this is one of the reasons that people are, for instance, interested in ReLU activation. This is not the only reason. There are lots of reasons. But one of the reasons that ReLU turns out to be a good guy is because when you go deep, it's always having gradient 1. It's just doing this impact of vanishing. This just makes it happen later, right, in deeper networks. Yeah? And people just started to see it through experiments. So one of the reasons is that ReLU has always gradient 1, and this gradient 1 is a good thing, right? We want to have it because it's going to help us avoid getting vanished or explode. Yeah? This is one point. And the other point is that this is one of other reasons that we did batch normalization, data normalization, things like that. Because once you do normalization, this is going to keep your values, the weights, in a kind of reasonable range. So that explosion or vanishing is going to happen again later. Okay? But again, these are not the only reasons. These are going to help in terms of vanishing, right? Questions? Everybody got clear about what the vanishing and exploding gradient is? So you can easily extend it to a more complicated network. Like you can think of one MLP, right? And all of those weights that I showed you here, they are going to be matrices, right? Now you're going to have matrices, and all of those derivatives that we had are going to be gradients. Now again, you have a gradient multiplied with a matrix, and so on. And all of these things like the explosion, or to just specify the weights, you can represent it in terms of eigenvalues. So I don't want to complicate this story here, but I just wanted to indicate that you can easily expand it, at least for MLP. It's not that hard to see it analytically that the gradient is always going to vanish or explode. Okay? Great. So now we know what the issue is. Now the question is, what is the solution, right? And there are a bunch of solutions that we have, like use better activations. For instance, just use ReLU all the time. This is one of the reasons people always use ReLU in CNN. And the other one is just use batch normalization. We already had this. But these are not obviously working as you go very, very deep, as we saw in the experiment by Microsoft, right? So they, of course, used ReLU. They, of course, used batch normalization. But it didn't resolve the issue when they went for 56-layer CNN, right? So this is when people started to come up with the idea of skip connection. And this skip connection is going to help us avoid vanishing gradient behavior. Okay? Questions? No question? Yeah?
So if we had a mix of, like, I mean, I guess one of our cases was a ReLU activation, all of our weights being larger than 1. If we had some, like, even if we had some of the weights being smaller than 1, it still wouldn't matter because it would still multiply way too big.
I mean, this is like, if you want to be very precise, theoretically, you can show that there is a sort of what we call it concentration behavior here. This means that it doesn't matter how you start. When you start something randomly, then they are going to somehow either concentrate around one point or another, right?
So it'll end up on
yes, yeah, either of them. And the point is that the chance of ending up around 0 is much higher than around infinity. And around 1 is pretty much the chances against 0, right?
But regardless, like, even if it's one or the other.
Yeah, because at some point, like those weights which are smaller are making the gradient smaller. And they're going to push those larger weights to get it smaller. And again, at some point, the whole thing is going to just drop.
Oh.
Yeah? I mean, just think about your gradient. Like if you have a function, when you compute the gradient, initial values of the gradient are very large because you are far away from the optimal point, right? But as you get close to the optimal point, the gradient itself is going to vanish, right? The gradient itself close to the optimal point is 0, right? Roughly 0, right? And then these values are going to make your weights and all of those partial derivatives to get very, very close to 0, right? And then, yeah, they push everything towards 0. Yeah?
Okay.
Yeah.
Thank you.
Yeah, Norse?
So that's the reason
Yes.
The end is close.
Is most of the time vanishing. Vanishing is a higher chance. I mean, and it's more challenging because if you have exploding gradient, okay, you could say I'm going to clip it. So if the gradient is larger than some value, if it is 1,000, then I'm going to clip it. No, clip it. It means that I'm going to say whatever is beyond 10, I'm going to treat it as 10.
Oh, I see.
Yeah? So that's going to be no issue, right? And at some point, it's going to start getting back, right? I can't avoid it because I have gradient. But vanishing is more challenging. I don't have any gradient. And I can not simply give some number, right? Because, I mean, in one-dimensional case, you just need to check positive, negative. But if you have a huge gradient vector, then it's going to be 2 to power that much cases, right? You cannot search it. Oh, clear? Questions? Yeah.
I'm curious about why the batch normalization for our features helps with the.
Because simply those weights that we have, they are going to get a small, like slower inside through the training process. Because you always normalize everything, right? You concentrate everything around 0 with variance 1, right? And this is going to help you to have weights which are closer to 1 in average. And then the behavior, the concentration around 0 is going to happen later.
Because the speed of weight updation gets slower.
Yes, yes. The speed of vanishing is going to get slower or explosion. But it doesn't mean that it's going to totally stop it. It could happen again, but it's going to happen in deeper length. Huh? Okay. So essentially, like if you don't do batch normalization and you don't use your ReLU, you would get even with like shallower network, 16 layer, you're going to start seeing the vanishing. But with that one, maybe you can keep on going to 20 layers. But then, again, you start to see that. So, questions? No question? OK, so let's just get started with the skip connection. This skip connection comes from the idea of residual learning. And what is residual learning? Let's just compare residual learning with the plain learning that we have done up to this point. So now, up to this point, we always talked about getting one input x, and then we wanted to learn the label y, right? So we're going to design our model somehow that it's going to get x, and at the output, it's going to give us y, right? So our neural network is getting x as input, and is giving us at the output the label y, right? And we just do the whole training to find out what is this function, correct? Now, this is what we call it plain neural network or plain modeling. So you just get your x and connect it directly to the output. But you can do something else. You can do residual learning. And this means that instead of learning the function itself, you just learn the residual, the difference between the label y and input x. And you might ask me right now, OK, x might be an image, y could be a class. So how can I just compute that one? Don't confuse yourself right now. Just think about the dummy example I gave you. We're going to later see how we can deal with this, OK? But right now, assume that x and y, both of them are of the same nature, right? Both of them are numbers, scalars, right? So I have a scalar x, I have a scalar y. I wanted here to find out what is the function between x and y. So instead of learning that, I'm going to learn what is y minus x. And I'm going to call it the residual function r. If I know what r is, x is going to inside r. It's giving me y minus x. And then I can add it up with x. It's going to be y, right? So the output of this residual unit, so this residual unit here, this guy at this point, is y minus x, right? Before the summation. And once you get also this summation, so x is coming here and getting added to the residual output y minus x, I'm going to have y. Everybody sees that? Everybody's clear? Right? So this guy that you see here, this is what we call a skip connection. Yeah? So it's just skipping the residual unit. It's just getting, or residual model, sorry. It's just skipping the residual model, the neural network, and it's just getting added up at the output, right? Now, the idea of residual learning is that, okay, if we can design such an architecture, maybe we do that, and it's going to help us in terms of vanishing gradient. And you might wonder why. So let's get back to our simple example, see what's going to happen if we just get a skip connection. Okay? So let me just consider this case. So I have x. Again, everything is as before, but before we didn't have this green skip connection here, right? We didn't have this guy. We just passed this input. It goes all the way forward, and at this point, it's going to come out. You're going to get theta, right? Now, the other case is that I'm going to get out of this guy x, and then I just do a skip connection. Now, this guy in between here and a neuron here is trying to learn y minus x, the residual value, right? And once I have the residual, then, theta minus x. Here is theta. Theta minus x is learned with all these neurons in between, and then theta minus x is added to x. Okay, I have also W1 here, so maybe I write it on the board. That's going to get it. So this units in between, so I have x here. Now I have W1 here, and then I start this skip connection, right? So this is going all the way towards the end, and at the end, this guy is coming here and added up to this output. Now I have theta. So anything between this, inside this skip connection, is just learning theta minus W1 times x. This is what we'll learn here. And then once you have W1 times x also coming here, so theta, what you get out at the output is going to be this guy plus W1 times x, which is going to be theta itself, right? Everybody's cool? Questions? So now let's just do the forward and backward pass and see what's going to happen here, right? So now if I start with the forward pass, everything is as before, right? I'm going to get W1, Y1, W1x coming out activated. And so on till YL minus 1, YL plus 1. YL plus 1 is now output of this last neuron, which before this, like in the previous case, it was the theta itself, right? Because we did not have any skip connection, correct? Now, since we have a skip connection, we're going to have this YL plus 1. And then how do we compute theta? We're going to get YL plus 1, this activated output, which is the residual value. This is this guy, the guy who is trying to just learn theta minus W1x, right? And then I add it up to W1x. It's going to be my theta, right? So this is the forward pass, the way that I just go forward, right? Now I'm going to start backward. So if I want to start backward, just look at this guy and tell me what would be the first one. So some people, my experience, is going to get confused here. So let's do the very first one together and the very last one together, and then the confusion going to get resolved. So yeah, let's say that I am here at theta, and then this theta is coming from YL plus 1. This theta is coming from YL plus 1. What else is going to compute theta for me? What else is computing theta for me? Just look at this guy. If I want to compute theta, what do I need? W1x, right? So I'm going to keep it here. W1x, right? And it's coming here. Now, I have here the derivative of loss with respect to theta. Now, if I want to compute the derivative with respect to YL plus 1, what should I do? How does the chain rule look like? Derivative of R loss with respect to YL plus 1. How many terms do I have here? It's not 2. 1. Great. Yeah? I need the derivative of R hat with respect to the guy who is immediate function of YL. You always look forward, not backward, right? So YL plus 1 is showing up where? In theta. Does it show up anywhere else? Does it show up anywhere else? Here. No. YL plus 1, the only mission it has is to compute theta, right? It's true that theta needs something else. We're going to get to it when we get very close to the first layer. But right now, if I want to just compute the derivative of YL loss with respect to YL plus 1, I don't need anything else, right? So I'm going to have derivative of R hat with respect to theta times derivative of theta with respect to YL plus 1. Do I have anything else? Do you think any other function exists where YL plus 1 is being involved? No. So I don't need to continue this one, right? So you can potentially, if you like, you can start writing down the derivative with any variable you have. But the derivative of that variable with respect to YL plus 1 is always 0, right? So they are not going to show up. So when I am moving backward at that summation point, I am not doing anything. It's exactly as before, right? Everybody's clear? Where do you think that it's going to show up? When I get very, very back here, right? At the beginning, where the branches are getting out, right? So let's do it together. You're going to see it clearly. So now I am going backwards. So theta is the immediate function of YL plus 1. So when I want to compute the derivative with respect to YL plus 1, I only need to care about theta, right? So it's going to be theta dash. Here, basically, the derivative of theta with respect to YL plus 1 is going to be 1. So theta dash is going to remain as before, right? So basically, the gradient is going to just pass backward directly to YL plus 1 without any change, right? Now, the next thing is that I'm going from YL plus 1 backward to YL. It's again like before, right? So from YL, I'm going to write it down, the derivative with respect to YL to be the one with respect to YL plus 1 times the partial derivative of these two. And it's going to, again, be the gradient that I had multiplied with the weight and activation derivative, right? And I keep on going backward towards this point, right? The point, the very first neuron. Everybody's clear? So nothing is going to get changed. Theta dash, the gradient of the output, was directly passed to YL plus 1. And then it's getting passed backward exactly as before, right? Till I keep on going like this backward till I get to the very input layer. So I got to the input, like this second neuron. The second neuron, I can again write it down as before. And now, at the second neuron, I have computed the derivative of R hat with respect to Y1. So I'm at this point, right? The derivative of loss with respect to Y1. And this guy is, again, the gradient that I had at the output times all of those terms. This is exactly the term which was vanishing for us, right? Everybody's cool? Now, I want to compute the derivative with respect to W1. And you need to help me now on the board. If I want to compute the derivative of loss with respect to W1, what do I do? What is the immediate function being involved with W1? What are they? Exactly. So look at it here. Y1 is coming immediately at the output of the first neuron, which is weighted by W1, right? So it means that Y1, the output of the first neuron, is the immediate function of W1. What else we have in this network? Theta itself, because theta is whatever we got out of the last neuron plus W1 times x, right? Everybody's clear? Now, if I want to write down the chain rule, how does it look like? Two terms, exactly. So one of them is going to be the derivative with respect to Y1, right? The other term is going to be the derivative with respect to theta. Great. Right? So these two terms, you need to consider both of them because both theta and Y1 are now a function of W1. So you're going to write it down in this form. This is the chain rule that you can write. And now you're going to replace the terms that you have. the first term, if I replace the first term, how does it look like? It's exactly that vanishing gradient we had, right? Because derivative with respect to y1 is the term we had before, right? It has passed all the way backward to the beginning. It has accumulated all the things we had inside backpropagation, right? So this term is going to be the same thing. What about this term? What is the derivative of theta with respect to w1? X, great, yeah? Is it vanishing? No. So if I replace it, this term is the one we had as before, and this term is simply theta dash x. Clear? Everybody's cool? Now, let me just replace that first term again as before. So that term itself was theta dash x something. So if you just do the math, you're going to see that you have this gradient of the output times input, gradient at the output theta dash, input x. So you have these two terms always. And then you have this term which is vanishing. This is accumulation with the backward propagation. And you have one single one here, right? Clear? Now, if I just look at this guy, you see that here I have this term accumulated by backpropagation, which could potentially explode or vanish. Most of the time it's vanishing. But we have one term which is not vanishing anymore, right? It's coming from the skip connection. Clear? Everybody's clear? Questions? Yeah? Sorry?
So because the derivative is always x, so wouldn't it, like, it would never change?
You mean this term is going to be always 1?
I mean after the term that's vanishing vanishes.
Yes.
We have the derivative with respect to theta, which is always x, right?
It's not always x. I mean, it depends on your output, right? Yeah. So when your x and output is changing, that derivative is also changing. But it's not a small value anymore. It's just something large, right? I mean, you're going to see that how we are going to incorporate it inside a real neural network. But here the point is that your gradient is not vanishing anymore, right? So now, any question? Was it clear? No? So it sounds like a very simple trick, right? But it's effective. It's working because it's just stopping your gradient from vanishing, right? It's just keeping some meaningful values inside your gradient, whereas in the other case, you always have vanishing terms, right? Now, this is the idea of a skip connection. So once you're backpropagating, if you have a skip connection, even if you go very deep, now you still have some gradient values. And in general, what we call as a skip connection, so a skip connection is actually a kind of link, is a kind of connection. It could have potentially some weights, and the weights could be potentially learnable. And they are connecting some layer, some previous layer to the next layer. Okay, so L minus S, so you are at layer L, then you can potentially go S layer before, and then you just connect the skip connection. Now, the typical approach is something like this. So if you think that you are in layer L, and now we stop thinking about very simple neural networks, just think of a general CNN, for instance, and that if you are doing very deep, you're in a general layer L, then the output, activated output of that layer is YL. ZL is the output of the convolution, or the output of the linear operation. And now, how you build the skip connection, you essentially do it like this. So you go S layer before. So you're at layer L. Say you're at layer 5. Then you're going to go, I don't know, 3 layers before. So you look at the activated output of layer 2. And then you get that guy. You might potentially multiply it with some weights, right? What is that weight doing here? I mean, there are multiple reasons for it. In practice, really, we don't use it at all. So we're going to fix the dimensions using the convolution idea that we know. But this weight here is that it basically wants to just fix the dimension. So if this YL, this output of the previous layers, is not exactly as the size of our linear computation here, the output of our convolution, then it's going to just get multiplied to this one to somehow change the dimension. But potentially, you can also learn it. So you can think anything inside this weight W, any entry here is a weight that you can learn, and then you compute the gradient with respect to, and then you update it, right? You could potentially learn it as well. But now, it's the primary purpose of this is that you want to somehow make the dimension matching. Anyways, you get the output of the S layer before, you multiply it to something, or just deform it, so that it can be added into ZL, and then you add it up, and then you do the activation. Okay? Everybody's cool? You got the idea of a skip connection, how you can do it? Great. So if you got the idea, once again, what is W exactly? So it's a weighted component, so you could potentially learn it, as I told you. Also, we can just set it into fixed values. Most of the time we try, if we just add it, we just want to make the dimensions matching. And one other thing is that you might ask why here we added the output of the activated output of the previous layers to the linear transform of the current layer, right? Why we added Y output to Z in this layer, right? Why, for instance, we didn't add it to Y, right? You get my point? So what I'm doing here, so I am thinking like this right now. So I have a convolutional layer network, for instance, and then I am looking into two layers. So here, this is layer L minus S. Okay? Here you are doing the convolution. So you had something before coming into it, and then you get at the output of this guy, ZL minus S, right? Then you do activation. For instance, you put ReLU here, and then you get YL minus S, and then you keep on going till you get to your layer L, right? This is your layer L. From layer L minus 1, everything comes inside this. You're doing convolution, and then at the output, again, you're doing activation, right? And here, the value here is ZL. The output is YL, right? What I am doing here, I am getting this guy, and then I'm connecting it here, right? Correct? I get this guy, I connect it to this output, then I do the activation, right? You might say why you didn't take this one and add it here after activation. Or why you didn't get this guy and add it here, or this guy added at the output. You have 4 different combinations, right? The answer is that there is no reason for that. Okay? So this was the initial proposal. In practice, you need to try all of them if it is really crucial. But it turns out that the whole idea is not that sensitive to this. Okay? This thing, this idea, like this kind of connection we have here on the board, this turned out to be the best one. But as I said, it's just a choice, right? You can try other ideas as well. The whole point here is that you have this skip connection, right? So the original idea that they did, they actually said that this, like, you connect Y to Z, this is the best idea, because simply they try different experiments. And one other point is that they actually didn't use any weight. So this matrix W here, it was simply identity matrix. Okay? They didn't use any weight, nothing to learn. Just simply get this guy and add it, exactly like what I have shown here on this board. And I think you did it already in assignment 3, right? Where you get this guy and just add it up. Yeah? Yeah, that one was residual network. Okay?
Capital weight, capital W.
Yes?
What
It's a bunch of separate weights. It doesn't have to do anything with those.
So for the specific weights, for example, like the L minus S layer, so it has no relationship with this capital W.
No, it doesn't have. So here what you do, here you simply think that this guy here, this one, is again a linear layer with weight W, right? This guy comes out of it, get multiplied, then it's get added, right? Then when you are back propagating, you compute the gradient with respect to weights here, 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 and also this guy, right? And I don't want to bore you, but you can simply do it. If you want, just solve the dummy example we had, and assume that the escape connection itself, that green connection, has also a weight. And then see how you can compute the gradient. I mean, the gradient immediately comes from the gradient of theta, right? Because that is directly connected to theta and nothing else. Right? So you can simply do back propagation on that. Questions? Yeah.
We don't learn it at all. What's the benefit of if you learn it? Is there
No, it's just increased complexity. It doesn't make any harm. Actually, in the very initial, I'm going to show it, but at the very initial one, they considered a general weight matrix. But it turned out that when it converges, it's simply identity. So they said, like, forget about it. You don't need to learn it. Yeah, but you can learn it, yes. It's just complexity. You need to do more computation, right? More weights, more computation.
help with accuracy?
It could potentially. I mean, if everything is done properly, then it should help. But it turned out that it's not doing any meaningful impact, right? Yeah. Questions? Everybody's clear? Okay, so I thought I'm going to finish the chapter by now. Not. So we're going to have a couple of minutes, 4 minutes break, yeah? And then we start with the rest of it, right? Okay, shall we go on? So now, this idea of skip connection that we had came up exactly the same study by Microsoft, which discussed this fact that deep neural networks are showing this vanishing gradient behavior. So that paper actually came up with this idea that we use this skip connection to build some sort of units. And that unit is what we call it the residual unit. Okay, so how does the residual unit look like? It's usually two different layers. And then you have these two different convolutional layers. You have the input also by a skip connection connected to the output of the very last layer. And this is what we call it residual unit. So it's going to help us go deeper inside the neural network. And I mean, that particular study showed that when you use the skip connection, now you can easily go very, very deep. If you don't have a skip connection, then you're going to get at some point at a bottleneck. At some depth, you cannot go any further deep. So this is the unit they suggested. So it's not like a must thing, but most of the time when we think of a residual unit, it looks like this one, right? So how does the unit look like? You got X, this is the input, and this is passed through one. This here weighted layer, this image here is exactly coming from the paper itself, okay? But here the weighted layer is simply either a fully connected layer, the linear part, or a convolution operation, right? So it's a linear operation here. Then you do ReLU activation. Out of that one, again, you do a linear operation here. And then at the output, you're going to get one linear output. Now you get your X, the very input to the unit, and then you add it up to what you got out of the linear, the second linear operation before you do the activation. So this is basically consistent with what I formulated in the other slides for you. Okay? So this is the original suggestion here. Now, for you, so most of the time we are going to consider the depth of this unit itself to be 2, but you can go deeper. That's totally fine. And if you want to build a neural network, you're going to just put these guys next to each other. So if you want to have a very deep residual network, you can get multiple residual units connected to each other, and then you're going to just have this one as the whole network. Now, this skip connection here, whatever is happening here, is this skip connection here. What it does, it basically get the input and add it up to the output of the second one, as I told you. The point here is that, so this fx is the second one, the end-to-end function here. The point here is that if you want to do this, if you want to add this output of the second weighted layer, if you want to add it to x, you need it to be exactly of the same dimension as this input, right? The output of the second weighted layer should be, if you don't consider any weight, right? This guy should be exactly of the same dimension, of the same shape of your input, right? So the reason that during CNN part, I just insisted so much on the fact that by doing zero padding, you're going to be able to fit the dimensions to what you want. This is the main reason. Because if you forget about this weight here, this W here, if you don't want to have W here, then you basically need to get the output of the second weighted layer, F. You want to be able to sum it up with X. It means that you need to have two tensors which are exactly of the same shape, right? If they are not of the same shape, you cannot add them up. And this was the reason that we use zero padding. This is the main reason if you do zero padding in residual networks. Yeah? You are not getting so much features out of zero padding. The only reason is they're going to make the life here easier. So as I told you, the way in the general proposal, you could put some weight for this skip connection, this W here. And this weight could be in general learnable. It means that you can, at the end of the day, compute the gradient with respect to that weight, and you try to update that weight in every single iteration. But in the initial study, they put a general weight here, and then they try to optimize it through training. And at the end of the day, they saw that this weight is going to be simply identity matrix, meaning that if you just remove this guy here, nothing changes. And because of that, they just said, maybe we can reduce the complexity. We simply consider fixed skip connections in practice. And this is usually the thing that we use in practice nowadays. But if you want, you can always do this. I mean, you can try it in PyTorch, right? Whenever you want to do a skip connection, don't simply add it. Pass it through one linear layer and then add it, right? And then when you write dot backward, all the backward propagation is going down. Those gradients are going to be also computed and updated. Everybody's clear? So this guy was the one who won the challenge, the ImageNet challenge in 2015. And you can click here to get to the paper. The paper is really interesting. I mean, this was one of the nice works, even though the idea is quite simple, but it's very effective. Yeah? And it somehow did a very big breakthrough inside deep learning, because now we can go really, really deep as we wish. Like nowadays, any clue what is the deepest ResNet we have? ResNet 1001? You can go very deep. Yeah? Residual network. I mean, have you heard of UNet? DenseNet. These are crazy deep networks, and all of them use skip connection. If you don't have a skip connection, forget about it. The gradient is not going to survive. Okay? So now, just to make it clear, we are going to just go once forward, backward, but I promise I'm not going to make it hard. Okay? So let's just see how the forward, backward propagation look like. If we want to just do forward, like if we are doing really CNN, then our input X is going to be one guy with C channels, right? It's a tensor with C different channels. I told you I want to add it up to the output of the second convolutional layer. So if I want to just go forward, that layer, how many filters does it need to have? C again, exactly. So I'm going to pass it through one convolutional layer with C filters. Now I'm going to have C different channels, right? And I just do right zero padding, side that. The dimension fits to the dimension of input. So this Z1 is going to be exactly of the same dimension of X, right? I can do it now, right? Now, if I do that, then the next thing is that I do the activation. Again, I want to do one other convolution. How many filters do I put in my convolution layer? Again, C, because I need to keep the depth of my tensor the same. So it's going to be another guy, bunch of other weights, C different filters. So I'm going to get Z2. Again, Z2 is of the same dimension as Y1, Z1, X. Perfect. And now I'm going to do the skip connection. So I'm going to add that Z2 to X, and then I do the activation. Yeah? Everybody's clear? Yeah. So this is going to be one residual unit. So the input X goes inside this unit. The output Y is coming out of that unit. Now, what if I want to just do backpropagation over that guy? So let me just look at this one. And let me first draw it on the board for you. And then I guess you can immediately see it. OK. OK. So we have X, right? This is the input. This guy goes to Z1, right? The output of the first convolution. This guy goes to Y1, right? This is the activated version. This one goes to Z2. Then I'm going to have this X itself coming and added here. So I'm going to have these two guys added. And they are making the final output Y, right? This is how it looks like, right? Now, if I want to move backward, I first get the gradient with respect to Y. So gradient at the very output. Where should I go next if I want to move backward? It's going to be Z2, right? So I don't need, again, like the dummy example, I don't need to care about that summation here, right? That doesn't do anything at this point, right? So I'm going to get from Y to Z2 directly here. So I'm going to compute the gradient of Z2. And the gradient of Z2, you can simply look at this guy. Now, I'm going to use this misuse of notation now, so to just keep the derivation simple. Now, always gradients are multiplicative. I just show that gradient, so you remember what we did when we were doing the CNN, right? So I'm going to do the same thing. So I'm going to say that the derivative with respect to z2, I just need to multiply with the derivative of the activation function. Because here in between, I get z2. X is also coming here. They add up and they get activated, right? Now, when I want to move backward, I just need to take care of activation, right? So at this point, nothing is happening. The next thing that I'm going to do, I'm going to get back from z2 to y1. What should I do here? z2 is the convolution output. y1 was the input. And if I want to move backward over a convolutional layer, what should I do? Another convolution, right, with reverse filter. So I'm going to do the convolution with reverse filter. I'm getting backward here at y1, right? Clear? Now, from y1, I want to get to z1. What should I do? Activation. That's just derivative entry-wise product. That's great. And I can do this. Now, what if I want to compute the gradient with respect to x? This is where skip connection is showing up. So what can I say here? I can say that this y is an immediate function of z1 plus x, and, sorry, z2 here. And z1 is also a function of x. So it's a convolution of x, right? Correct? So x got convolved with some filters, C different filters. It gave me z1. And y also is being computed directly from x. Now, if I want to write down the chain rule, how many terms do I have in that chain rule? 2 terms, right? One of them is the term which is taking care of y. The other term is the one which is taking care of z1, right? So if I use this misuse of notation, I can write it down in this form. So the gradient with respect to x, first I'm going to take care of z1, the first guy. So it's going to be the gradient of loss with respect to z1 times gradient of z1 with respect to x. So it means that I am just moving backward from z1 to x. And if I want to move backward only from z1 to x, what is it? It's a backward convolution, right? Just convolve with the reverse filter. And the other term is y itself. So it's going to be gradient with respect to y times the gradient of y with respect to x, right? So y is here. So this is the second guy. So I'm going to say x is also connected to y. So I'm going to take care of that one with the second term, gradient with respect to y times gradient of y with respect to x. That is not a complicated thing for you, because x is showing up in the argument of an entry-wise operating activation. So it's going to be entry-wise product again, but you don't need to care about it always. In practice, you are using some platform which does it for you. Important thing is that you need to know which terms of gradient are showing up now, right? Everybody's clear? So backward propagation is exactly like you're moving backward at over 2 convolutional layers. The only difference is that when you get to the very input of the unit, you also have one other term coming directly from the output. So the gradient is also somehow skipping these 2 convolutional layers. Questions? Everybody's clear? Yeah? Do you have the feeling that efforts on backpropagation is now paying off? Because do you see this like, really, do you see it immediately? Is it now obvious for you? Because if this is obvious for you, congratulations, you are very perfectly seeing what is happening inside deep neural network. This is the only thing happening, right? Gradient is just propagating. And whenever you see an issue, gradient is not going on. So you need to just fix that, right? Everybody's clear? OK, great. So that's it. So you can write it down, as I said, as a backward convolution. That is easy. This one is simply entry-wise product. You really don't need to, I mean, you can try at home to double check it, but you really don't need to get all the details anymore, because you already see how the gradient is propagating backward. So that's it. And a residual network, if you get these residual units that I showed you and you put them next to each other, a couple of them, then you're going to have a residual network. Okay? And have you heard of the classical ResNets in practice we use? Numbers, ResNet 18. Okay, it's shallow. ResNet 34, ResNet 154. And as I told you, you can go extreme, ResNet 1001, right? So, and those guys are having like 18. You basically can just get 9 different residual units because every single of them has 2 different convolutional layers, right? Then you go very deep, right? So that's the idea. So you just cascade these residual units, and you can now go very deep. You can also add them to other type of networks. So if you are to design your own network for some specific purpose, maybe you can put some residual unit, yeah, or multiple of them. Then you put a convolutional layer. Then you put fully connected layer. That's up to you. The only thing you need to take care of is that you fit the dimensions, right? That they are going to pass, right? And you need to be able to move backward, right? If anything is of the units, you know, like a classical fully connected layer, if that is a convolutional layer, if that is a pooling layer, if that is a residual unit, you always can move backward. You do know. I mean, I do know that you don't do it personally. I mean, PyTorch does it for you. But you know as the designer that it's possible to move backward on those architectures efficiently. And then you can simply use them. That's it. And so you can just use any other kind of layer in combination with this kind of unit. And again, you can add any sort of those other tricks we use in the previous chapters as well. You can add dropout in between. You can add batch normalization before, after them, or even inside them. That's totally fine. So in the original proposal, batch normalization was being used after every single convolutional layer. So it means that after every single of them, they were also using a batch normalization. You know? And it was because they wanted to just combat vanishing gradient. I mean, batch normalization is a kind of must there, right? So that's it. And if you have a residual network, people usually call them ResNet, and they are mainly based on this residual units. They are a kind of, you know, classical benchmark nowadays. So if you want to have one architecture for visual application which is working very well, ResNet is the thing. Okay? Questions? No question. Great. So now, if you look at the original paper, so in that paper, okay, I have put it again here. You can click here. And in that paper, they did actually a very nice experiment to somehow show the impact of skip connection. Now, here what you see is that you have 134 ResNets. So it has 34 different convolutional layers. And they are being, every 2 of them are being skipped, right? And these skip connections are somehow giving you the bypass to move backward, right? The gradient can efficiently move backward. So they consider this architecture the same architecture, but it has no skip connection. Okay? And the last one is VGG, I guess, I don't know which one. I think it's VGG 19, the deepest architecture they had in VGG probably, right? So VGG 16, sorry. This is VGG 16, the best architecture actually they had in VGG, the previous winner in 2014. And now they started to somehow go from this guy, 16 layers, to 34 layers. When it's plain, by plain I simply mean the second guy. No skip connection, right? When you do it plain, then the value is actually a bit increasing, the value of the error in both cases, right? This is top one. Like if you just take the largest first one, and then if you just check in the largest 5th one, error. So this is the top 5. And then you see here that this one, in both cases, doesn't matter. When you go deep, but you are doing it very naively, plain, then you are not gaining anything. Actually, you are getting a bit of degradation here, right? But as you go with the skip connection, now you can drop, right? So there are 3 different combinations they considered, basically by playing around with the batch normalization places and the kind of skip connection places and things like that. And at the end of the day, they are dropping with factor 4 here, right? Which is something. At least we are dropping. You're not going up anymore, right? And this was not anymore overfitting. So this was obvious that, you know, the story of overfitting, not being overfitting, is over as well. Because here again, as you can see, these are the results for training. And as you can see, when you are using plain network, your training loss is still going above the 18-layer network, which means that your model is not getting trained properly. It's not simply overfitting. I insisted on that point, I think, enough number of times that it's clear for everybody. But here, as you can see, after training, we are going, when we make it deeper, the training is going below the shallower network. This means that the training is happening properly. Vanishing gradient is not anymore the case here. Everybody's cool? Once again, I mean, I insisted here again, it's not overfitting, right? If you don't see it immediately, I'm going to kill myself because I said it 1,000 times, right? But I'm pretty sure that everybody gets it right now, right? Okay. So now this is the result that they showed in the ImageNet challenge. So as you can see here, these are the results for VGG, which was before, and this is the result for GoogleNet. These are the winners of 2014. And here they were now able to just go very, very deep. And you see, as they are going deeper and deeper, here the error is just dropping more and more. So the top 5 is the classical one which we use, and this is going to get into 4 point something. If you remember, we started in 2010 with 28% error, right? And now we are getting below 5%, right? Great. So that's it. You see? So this was the breakthrough. So you could just come up in the number of depth. At this point, people saw that you can go hugely top on the number of depth, but this is not going to drop. But then it turned out that it's going to drop, right? So if you just use skip connection. So even though the idea is quite basic and simple, it's very, very effective in practice. Questions? No question? Okay. So if you got no questions, so ResNet is not the only architecture with skip connection. So you don't need always to just skip 2 layers. You can do it in different forms as well. So there are a bunch of other architectures being proposed. So one of them is, like the famous ones are DenseNet and also UNet. And UNet is, like, again, one of those things that nowadays many people use in many applications because it is a sort of autoencoder. So it can do encoding and decoding for you, and it has a latent space in between. We're going to talk about autoencoder in Chapter 8, so no worries about that. But this is a kind of thing that in many image processing, spatial segmentation applications, people use nowadays. And again, it's using skip connection, right? So there are 2 types of skip connection in practice. Some of them are called short ones, which are basically those we use in ResNet. So you're going to skip just a few, and then you always do that all across the network. But there are also some long skip connections, like here. You see, like, you can connect the very first layers into the very last layers, right? And usually very advanced architectures somehow use a mixture of them. Like here in the DenseNet, you have the very long ones, and also you have the short ones. And they are really helping in terms of vanishing gradient. So now, if you're interested to try that, you can simply use PyTorch. You have the model pre-implemented. And now that you do know what is ImageNet challenge, most of the things that you have in PyTorch pre-implemented and pre-trained are somehow adapted for the ImageNet dataset. And the reason, obvious to you, right? Because of challenge, right? Because all of those models were initially being proposed to just participate inside that challenge, and they just got developed for that data set, right? So most of things that you have in your data in PyTorch, they usually get the inputs, which are 224 by 224 tensors of 3 channels. This is because images inside ImageNet are of that dimension, right? And then they usually have 10,000 output classes, again, because ImageNet has 1,000 classes, okay? And if you want to just use ResNet, just import these Torch Vision models and then try to call ResNet. And you're going to see like all that famous ResNets are already pre-implemented. Not only pre-implemented for you, it means that when they are pre-implemented, this means that when you call that model, you're going to get the whole neural network. The neural network is going to get, what is the input of that neural network? Images of what size? This one, right? 3 by 224 by 224. The output is going to have 1,000 classes, right? Output of the sigmoid with 1,000 classes. So you're going to, softmax with 1,000 classes. So that is the case, but if you want to try it for your own application, you can just play with the input and output layer, right? Nothing in between you need to change. Just change the size of the input layer and the size of output layer, right? Remove the softmax, add one smaller linear layer to just drop it into the number of classes you want, and then you pass it through softmax, right? So you can use those pre-implemented ones, and better than that, you actually have the pre-trained weights. So if you just, this slide is for 1 year ago, so maybe there are new updates here. I don't guess so, because this is a quite well-defined problem. But you can access ResNet, you see here, and once you're inside ResNet, you can already just set your weights to be the predefined weights. These weights are the one which people got after training for quite some time, right? So they are already working very well on ImageNet. And there are different versions because different people tried their own training, right? You can just load them. And now if you give ImageNet sample into this model, you're going to get a very good performance at the output, right? But you might ask me that what if I have another application? For instance, I want to use this, but I don't want to use it for ImageNet. I want to use it for MNIST. Should I just start from scratch? So does it mean that those pre-trained weights do not help me? The point here is that this is true that if you just modify your architecture with the weights that are trained for ImageNet inside your pre-implemented model, this pre-trained model, if you now modify the input and output to get the MNIST working with that, and you give the MNIST image, that is true that is not going to perform perfectly, but the point is that if you start from those weights and you keep on training your model, this is going to converge to the optimal model, or not optimal model, the right model, very quickly. Okay? So the key point here is that if you start with those weights which are suited for ImageNet, and now you start to train your architecture for MNIST classification, it's going to just converge much faster as compared to just starting with some random weights. And you might wonder why this is happening, because those weights are having some information about the idea of image classification, right? And the patterns you need to detect inside images to be able to do the classifications are not very different, right? It's true that the images themselves are different, but the pattern you need to detect to be able to talk about those images are not different. And because of that, if you use those weights, they are going to get very quickly converging into the right weights that you need for your own application. So this is somehow the idea of transfer learning. The transfer learning tells you that if you have two applications, MNIST classification, ImageNet classification, and you are training one model, you're just finding the weights for one of them, then if you take that guy and bring it here into your other application, then you can easily modify this model, transfer this model into a right model that does this this task properly as well. Yeah? So what you do here, I mean, if you do what I told you here, it doesn't mean that you're actually doing transfer learning, but the theory behind it that is making this thing converge faster or guaranteeing that is happening is what we call a transfer learning. If you are interested, you can just take a look at this online. So, any questions? Yeah.
About this, what's it called, the skip unit thing.
Yes.
So, like, because of that extra term, we don't have the vanishing gradient problem, right? So
Yes.
why can't we just use like one skip unit for a whole?
Because that one skip unit, like if you have a very deep neural network, right? So as we saw in the dummy example, like anything in between is not seeing the impact of a skip connection, right? Only the guy at the very beginning is seeing that, right? So it means that the vanishing gradient could happen in between for those layers, right? So you need to have them as well, right? But those long connections are also a thing in practice. Other questions? No question? Okay, so that's it for ResNet. As I told you, this is the practical one, so it's not like history anymore. You use it in practice for many applications. And the skip connection idea is quite good. Next thing that we are going to do, we are going to talk about recurrent neural networks, okay? So for recurrent neural networks, 2 points. First of all, in recurrent neural networks, now we are going to somehow launch from classical machine learning or deep learning into the case where we are dealing with sequences. And dealing with sequences, we really don't need to develop any new modules like convolutional layers or anything. We just use what we know, but now we want to deal with the data, which is just going over sequence, okay? So if you want to make your mind up before the next session, you can take a look at these slides. I'm going to discuss it in details next session. So in practice, you could have sequences like when I'm talking, right? And the information I'm giving you, this is a sequence of information, sequence of words, right? And this sequence of words have some sort of temporal connections, right? The word I say now going to decide what would be the next one, right? I cannot say anything after one word, right? And this kind of behavior, even though the deep learning in this one-shot approaches, like I give the whole image into it and it can tell me what is the class of it, this was again a kind of challenge to make this architectures work when you have a sequence of data, right? Because in that case, you're not dealing with one data and then the other data is totally independent of that. You're dealing with one word and the next word is depending on that one. So we're going to see in the next chapter that what is the issue here? What is the issue of having a sequence? What kind of problem that temporal thing can make us? This is the first thing. The second thing is that we're going to see that what we need, which is the memory, and we want to make a memory, and the most basic idea is to just use a recurrent neural network. This is the main topic of the next chapter. So once we go towards the end, we're going to have one part which is about the one-to-one correspondence problem. I don't expect that you understand it right now, but you're going to understand it once we're over with that chapter. So that one is a kind of bonus topic that I keep when I have time. I just skip when I don't have time. So my expectation is that we don't have time this semester. Usually in falls I have time. We're in winter, right? In winter I don't have time. But if I had time, I'm going to do it. If not, I'm going to give it to you. This is something not sophisticated, like it's a bit old-fashioned, but it's very interesting in terms that you can build your analytic mind. And then after we finish with that, we are over with anything in classical deep learning. And then we go for a couple of topics. Seg-to-seg models, Chapter 7, and autoencoders, Chapter 8. I try my best to just show that anything that you have learned in the course, you can use it in practice in very advanced problems. And then hopefully it's going to give you self-confidence to just go for more complicated adventures, okay? Just because we had a couple of minutes, I wanted to give you the overall perspective of the next sessions, okay? So see you on Tuesday. Thanks.